In today's video, I'm going to go over a newly published paper, which is the Approximate Gaussian Variance Inference, or in short, AGVI for state space model. Now, what does AGVI provides? Using AGVI, we can handle aleatory uncertainties that are inherent in the data. And we can do it online, meaning that as new data point comes in, we can refine our knowledge of our uncertainties. We presented our approach, AGVI, in the context of state space model. So before going into the method, let's take a quick overview of what the state space models are. State space models are probabilistic models that are mostly used for analyzing time series. For example, if we have a time series like that, as shown in the left figure, we can obtain what are the underlying patterns using several different components. For example, we can obtain what is the baseline of the time series, we can obtain what are the periodic pattern of the time series, as well as we can decouple what are the residuals that are present in the time series. Now, decoupling the residuals is very important because we do not want residuals to be present in the pattern, and vice versa, we do not want any patterns to be present in residuals. So the residuals should only contain random events that cannot be identified. So there is no pattern that exists, and because they are random, we cannot identify or model them. We can only obtain what is called an uncertainty bound for these residuals. Now, in state space models, these residuals are modeled using an autoregressive process, where the transition equation is this, where the XAR hidden state at time t is equal to phi, which is the autoregressive parameter, times the XAR hidden state at time t minus 1 plus Wt, which is the process error. Now, this process error term is modeled as a Gaussian distribution with mean 0 and variance sigma square W. Now, this sigma square W is known as the process error variance parameter, which is quantifying the aleatory uncertainty that is present in the residuals. Now, before going into how we can infer this variance parameter online using our approach, let's start with a simple time series to understand what is, or how do we model the aleatory uncertainty. Let's take a simple time series. For example, the black line shows a simple sine-like function. The red dots represent the data, and this is the aleatory uncertainty that is present in this data. Now, there is a variance parameter that will quantify what is the aleatory uncertainty in this data. For example, if we obtain a larger value for the variance parameter, then we'll be underfitting our model, or if we obtain a smaller value for the variance parameter, we'll be overfitting our model. This is not what we want. We want to identify what is the correct aleatory uncertainty that is present in the data. So we need to infer or obtain the right value for the variance parameter. Now, let's just remove the function and look at the residuals alone. Now, this violet region over here, this is the uncertainty or the aleatory uncertainty that we want to quantify. The residuals here can be assumed to be coming from a Gaussian distribution with mean 0 and variance parameter sigma square. So this sigma square, the variance parameter, is quantifying the aleatory uncertainty as shown by the violet bounds. Now, if we have all the residuals available to us, we can use the empirical variance formula in order to compute our empirical variance. In this case, since mu is 0, so it is mean centered, so we can remove the mu, so it eventually becomes this formula, where the variance is basically the average of all the wi squared. So all the residual term that you see, you square them, you take average, and you find your empirical variance. Now, in the case that we have large number of samples, for example, when t goes to infinity, this sigma square value will tend towards what is the theoretical value, that is the expected value of w squared. Now, this procedure is neither Bayesian nor online, because in order to use the empirical variance formula, we need all the residuals to be available to us. In case where we want to do it online, meaning that we do not have access to all the time series or all the residuals at once, here we are only observing the first data point, and we will be observing one data point at a time. Okay, so in this situation, we do not have an exact knowledge what should be the sigma square or the expected value of w square, so we only can start with a broad prior for the expected value of w square as shown by this figure here. Now here we are now observing only the first observation using the prior for the expected value of W square. Let's just skip this distribution over here and we'll come back to that. So using the prior for expected value of W square, we can obtain a posterior for the W. Now W is a distribution, or to be precise, it's a Gaussian distribution. Now if you look at the formula again, so sigma square is equal to the expected value of W square. Now we still need to obtain what is the distribution for W square, as you can see that now W is a random variable itself. So how do we obtain distribution or the moments for W square? In our group, we have developed a method that can provide a solution for this. So using this method called Gaussian multiplicative approximation that can provide the moments for the product of any two Gaussian random variables as shown here, and it is approximated to be a Gaussian random variable, we can obtain all the moments, that is the expected value, variance, as well as the covariance for the product of any two Gaussian random variables using closed form algebraic expressions. So using GMA, we have the solution for W square. So from W, we move to W square. So we use the distribution of W, use GMA, and obtain the posterior for W square. Now we have also found out another way to connect W square to obtain the posterior for the expected value of W square. So as you remember, we started with a prior distribution for the expected value of W square, and after that we obtain a distribution for W, then using GMA we obtain a distribution for W square, and now using the posterior for W square we have obtained a posterior for the expected value of W square. Now from this figure, if you see, there's not much difference between both the prior as well as the posterior, because we just observed one data point. So there is not much information to learn from that one data point. But as we see more data point, you'll see that the distribution for the expected value of W square is moving closer to what is the true value, which is denoted by this red dotted line. And also the uncertainty is shrinking, showing that it is becoming more confident towards or moving towards what should be the correct value. And by the end of the time series, it totally identifies what should be the correct value for the expected value of W square that is present in the data. And the distribution is almost like a direct delta, meaning that it has converged to the value of expected value of W square, where the uncertainty is almost negligible. Also from the data, we can see that in the beginning, because we started from a broad prior, the uncertainty was quite large, but as we observed new data points, it learned or refined the knowledge of the uncertainty, and eventually it learned what is the correct value for the variance term, quantifying the aleatory uncertainty in this data. And finally, we obtain what is the correct aleatory uncertainty. Now this approach or this framework where we connect W to W square first using GMA, and then from W square to expected value of W square. This framework we refer to as the Approximate Gaussian Variance Inference, or AGVI. Now it involves, I just want to repeat that it involves two main steps. One was connecting W to W square and W square to expected value of W square. Now AGVI is a Bayesian approach, and we have seen that we can do online inference for the variance parameter, and the best part is that all the computations that are involved for the two main steps, from getting the posterior of W square and then using the posterior of W square to update the knowledge of expected value of W square, we can do it analytically, meaning that all the moments, the expected value, variance and covariances, everything can be done using closed form algebraic expressions. Now again, the devil is definitely in the detail. All the proofs and formulations are provided in our paper. Let's move on to an example, and this is the case study that we provided in our paper, and this is a linear time varying case study where in state space model we have a transition equation as shown by this equation here, where x, the hidden state at time t, is connected to x at time t minus 1 through this term at, where this term at is a function of time itself and it has its own function. and plus WT, which is the process error, and this process error is modeled again using a Gaussian random variable with mean 0 and variance sigma squared W. State space model also has an observation equation where the observation at time t is connected to the hidden state at time t, and also connected through this function ct as shown over here, which is also a function of t, hence it is time varying. And it has an observation error v. So this observation error v is also a Gaussian random variable with mean 0 and variance sigma squared v. Now in our case, in AGVI, we consider that the R is either known from measuring instrument precision, or we think that the R is completely negligible, and we model all the aleatory uncertainty in the data through our process error variance parameter. Now, in this case, we have considered that the Q and R to be equal. So sigma square W, for example, the true value is shown using the red dotted line, which is like 0.42, and we have considered sigma square V also to have a similar value in order to see how the impact is. Now, from this, we can see that the black line, which represent our expected value, and the violet region shows our uncertainty bound. We can see that starting from some arbitrary values, we are able to retrieve what is the correct value for the sigma squared W. And we have repeated for other cases, for example, a slightly larger value with 1.35, and we see the same thing. Starting from some arbitrary value, we reach or identify what is the correct value for the sigma squared W. And we can also repeat it for other values, for example, larger values, and we still see the same trend where it correctly identifies what is the correct value for the sigma squared W present in the data. Now, we have also done other tests in order to see if our filter is still consistent or not. So first test that we did was we used this metric, which is NEES, which is normalized estimated error square. So basically, using this metric, what we have to do is, if we choose a confidence bound, for example 90%, 95%, and based on the length of the time series, we can identify what are the theoretical values. There would be one theoretical value of the number of points that can lie beyond this lower and upper limit. And in our study, we see that we satisfy this requirement. All the details are provided in the paper. And if you want to know more about this metric, you can follow books on optimal or control theory. We also did an empirical test to understand if our uncertainty for our error variances, which are basically the violet region here, are consistent or not. And for that, we have shown in our paper that for 1 sigma, 2 sigma, and 3 sigma, we show that what are the percentage of points where the true value lies within the uncertainty bounds. And we see that it satisfies the theoretical values of 68, 95, and 99%. We have also carried out a test because, as I mentioned, using AGVI, we assume that the R matrix is known, and we capture all the aleatory uncertainties through the Q matrix. Now, in most studies, there is a relationship between the Q and R, and we see that if the Q and R value is around like 10 or higher, it can give you a perfect value, or it can infer the correctly sigma squared W using AGVI. Whereas if the Q and R value is smaller, our sigma squared W value can be biased, and which is an important inference that we saw from our test using our method. So this is important to consider. So basically, we have conducted all the optimality tests. We have checked that our uncertainty bounds are consistent, as well as in our paper, we have shown that our error variance parameters are unbiased, which we have shown using by conducting t-tests. We have also compared AGVI with two other competing methods. So one is a Bayesian online method, which is SWVAKF, which is sliding window variational adaptive Kalman filter, as well as a correlation based approach, which is the measurement difference method. And we have compared using the metric root mean square, and then we have compared across several values, for example 0.42, 1.35 and 18.75, and we see that on RMSE we are much better compared to the other two approach. And if you look at the time, we are at least 2 orders of magnitude faster than the two competing approach. Hence AGVI is an online approach that provides consistent estimates, is accurate and faster compared to the other two competing approaches. Now, till now we have only tackled the univariate case. What about the multivariate case? Let's take the similar example. Here we have two different time series, and you can clearly see that the variance parameters for both these time series are different. Here it is smaller, here it is slightly larger. Now, as previously, let's remove the function and look at the residuals alone. Now, these residuals can be assumed to be coming from a Gaussian distributions where the mean are 0 and variances are sigma 1 square and sigma 2 square. Now, if I plot the joint density, considering that both these residual terms are independent, or the processor terms are independent, it will look something like that. In this case, we can model each of them like the univariate case, and we can extend it to multiple sigma square because there is no connection between them. So we can model each of them independently using the univariate formulas that are present in our paper. But in most practical cases, this might not be the scenario where W1 and W2 might have a correlation and the joint density might look something like that. In that case, the covariance matrix would look something like that, where in the diagonal we have the variance terms and we'll have off diagonal, which are the covariance terms between the W1 and W2. Using AGVI, we can infer the variances as well as this covariance term for the 2x2 metric. Now, what about higher dimension? So in 2x2 metric, we can evaluate both the variances as well as the covariance term. Whereas in higher dimension, for example, if we have process errors W1 till n terms, so we have n terms of sigma square variance parameters to infer. The Q matrix would look something like this, where there will be the diagonal terms, the variance terms on the diagonal, and we'll have all the off-diagonal covariance terms. Unfortunately, it is not straightforward, and because the Q matrix becomes non-positive semi-definite. And in order for Q to be PSD, it needs to be symmetric and all the eigenvalues needs to be greater than or equal to 0. Now, in order for the Q to be PSD, we need the Zolewski factorization in our approach so that we can keep the Q matrix to be positive semi-definite at any time t. In Zolewski factorization, this is normally the formulation where Q matrix will be obtained using, for example, an upper triangular matrix. We do the transpose and then multiply with the same upper triangular matrix. And this is the operation which is the Zolewski factorization. And this helps to keep the Q matrix PSD. In our case, since Q itself has all the variance and covariance terms as random variables, the L in our case will also be an upper triangular random matrix because all the elements will also be random variables. For example, let's consider ABC to be the random variables or the elements of the random matrix L. So it will look something like this, where Q will be equal to the L transpose times L, where all these A, B, and C are the elements of L. And eventually we'll obtain this matrix where we have these terms A square, AB, BA, B square plus C square. Now, let's consider that A, B, and C are all Gaussian random variables, and let's substitute in this metric multiplication. So it will look something like that. So eventually we'll end up with these terms where we have to do a square of a Gaussian random variable. So we have a product of two Gaussian random variable as well as squares of Gaussian random variable plus the square of another Gaussian random variable. Now, we already have the solution for this using the Gaussian multiplicative approximation, or GMA, where we can obtain the closed form expressions for all these squares as well as the product of Gaussian random variables. Hence, we can do these operations using closed form algebraic expressions. Now, this is what we do in AGVI for higher dimension, is that we do not infer Q directly. We start with a prior for the L, and from that we build our Q matrix. And at every time we start with a prior for L and we obtain posterior for L, and we keep building our Q matrix from this upper triangular random matrix. Let's take a quick example for the full covariance matrix. For example, if I take an example of the Q matrix to be something like this, so these are the variance terms and we have the off-diagonal covariance terms. So now we are inferring this term over here, the variance term, which is 2. So on the left figure, the true value is shown by the red line, the black line shows our estimation, and the violet region shows the uncertainty bound. Now we can see that starting from some vague prior knowledge, we were able to retrieve what is the correct value. Similarly, I can repeat this experiment for another variance term, and we can see the same phenomenon. Starting from some vague prior knowledge, we obtain what is the correct value, as well as for covariance term, and we see the same phenomenon. We are able to retrieve all the variances and the covariance term. So the bottom line is that we are able to infer all the variances as well as the covariance terms accurately using our approach. In conclusion, AGVI, which is the Approximate Gaussian Variance Inference, is an analytical approach, and we can obtain the error variance terms online using our approach. Using AGVI, we can infer all the variances and the covariance terms, and we can do it like for a full covariance matrix. And we have seen with our comparison with the other two competing approaches that we are accurate. We provide consistent estimates through our consistent estimates test that we have done, and we are much faster compared to the other two methods. And at last, the package is available online, and you can download it and you can use it in your project. Thank you.